Hi. So I want to give kind of a higher level talk about an issue that I feel like feels very important to basically kind of the future of natural language processing, and specifically like the potential of deep learning to really revolutionize this field, which is specifically what is this relationship between the computational fields like NLP and machine learning and deep learning and more traditional studies of language like linguistics and cognitive science. So it seems obligatory to acknowledge that deep learning is taking over NLP. You can see this by looking at, for example, papers published in ACL, the main NLP conference, when it first started in '79, or in '87, or really just in total over all the years leading up to 2015, and looking at the kinds of topics that we used to discuss for the through the history of the field, and then comparing that to the topics that have been discussed in just this most recent ACL last year. And it's really clear that neural networks and deep learning have taken this prominent position in the way that we approach language understanding problems. And this kind of enthusiasm is not unjustified. So like if you look at what are considered to be very standard tasks in NLP, things like language modeling and dependency parsing, and kind of higher level language understanding tasks like sentiment analysis and machine translation, and you compare the performance of deep learning models to our more traditional methods like graphical models or feature engineered systems, you can see that very consistently the even fairly naive neural network models will give a sizable boost in performance over traditional approaches. And state of the art is well beyond the results I'm showing here. These were very early applications of deep learning to these problems. And so this was exciting, and it's kind of like spurred interest in what are kind of higher level NLP tasks. So not things like language modeling and dependency parsing that we expect machines to do, but more things that look like how humans think about language. So as Sam was talking about this morning, one of my favorite tasks is the idea of like natural language inference, or RTE as we call it, for recognizing textual entailment. And the idea here is you want to be able to read some piece of text, like a sentence that, for example, says, a man inspects a uniform of a figure in some East Asian country. This is taken from the SNLI data set that Sam was talking about. And you're trying to decide whether or not a man is sleeping, right? And so we call this the premise and the hypothesis, and we want systems to say whether the premise entails the hypothesis. So kind of a true or false output. So this task has been around for 10 years or so, but there's been this kind of surge of new interest, specifically when Sam released this SNLI data set, so 500,000 training examples for this task. And this is models on the leaderboard as of yesterday when I checked. So you can see that when the system, or when the data was first released, the best system was getting 77%, and now we're at just over 86% on this sentence entailment task. There's a similar story with this reading comprehension task. Again, it's a really natural task that humans do well and we want systems to do. The idea here is you have some question and some passage of text that presumably answers the question, and you want the system to be able to output the answer to the question. So Percy Liang's group released data for this about a year ago, and you have this similar scenario where there's a leaderboard, and you can see that every month the best performing system is doing better and better and better on this task. So there's lots of reasons that people within the NLP community have kind of taken a step back and wondered, should we care about linguistics anymore? And you can look at the data and you can look at all of these tasks that were once thought to require really deep linguistic knowledge, and you can see that deep learning systems, which have fairly minimal insight about language, so they're usually taking raw text as input, very little feature engineering or knowledge about syntax or structure or semantics in any deeper sense. And they're getting good performance. And I think it's uncontroversial to say that, as is without linguistics, we are doing a lot of tasks and we're doing them very well. But the issue, or the reason that people aren't comfortable yet saying, no, therefore we don't need linguistics, is if you start trying to figure out what exactly it is that these systems are learning. We know they're learning something because they're able to do these tasks well, but what exactly are they learning? So if you look back at, for example, this SNLI data set, the system is trying to infer that the premise contradicts the hypothesis, and it seems that there's something deep that needs to be understood here. Something about, well, if the man is inspecting, then he has to be kind of like active and alert, and that precludes the possibility that he's sleeping. And that seems like really cool, like if we could get systems to pick up that kind of knowledge. But if you look a little closer, and specifically if you look just at the sentences within this data set that contain the word sleeping, 86 or 83% of them are contradictions, which means that if a system says I'm just going to assume every sentence that contains the word sleeping is false. It's going to get 83% accuracy on these sentences that contain sleeping, which is obviously not something true about language or that we want systems to know. But it will allow you to do well in this data set. And keep in mind that the current state-of-the-art performance on this data set is 86%. So it starts to look like there's some statistical anomalies you can exploit that will make it look like you're doing very well in language tasks, but you're not actually understanding language. And there was a similar result that was shown in the this past year at EMNLP for this reading comprehension data set. So this is the same group that actually put out the data set, Percy Lang's group, and they showed that if you take these inputs and you basically append some random sentence to the end of the passage that's unrelated to the answer, that this significantly affects the performance of systems. So systems that are getting state-of-the-art performance on the original data set in the 80-90% accuracy range, when you just add this random sentence to the end, they lose half of their accuracy, right? So again, unsatisfying because this really shouldn't affect the meaning of language or the ability to answer questions, and it seems that systems get confused by very shallow manipulations of the data. So this has kind of caused a reckoning of what is it that we want the systems to learn, right? It's like for a long time, and I've had a lot of discussions, I think, with people in NLP, NLP kind of pitched itself as an engineering field distinct from linguistics, right? So we say that our aim is not to explain how language works, it's to build tools that can do useful things with language. And you can see this when we do stuff like exploit preprocessing, regular expressions, HTML structure, multilingual context, all these things that aren't natural ways that humans learn about language, but we're perfectly okay having our systems learn that way, and I think that's fine. There's nothing wrong with saying, I want to do well on tasks, right? But I think the trend is changing, and people don't just want to do well on tasks. They want to do well on language in a more general sense. So I'm thinking of things like pre-trained word embeddings or task-independent sentence embeddings, general things like knowledge representation and grounded, multimodal embedding spaces, things like that. And there's just been this flurry of interest in these types of topics in the past couple of years. And there's something, I think, very important about this shift, because now we're going from saying, I want to do tasks well, to I want to represent language well, and that's a fundamentally different problem. And specifically, it's a problem that we really share a lot in common with linguistics. So actually, this is from the website of the RepEval workshops. This is a workshop that's been held in conjunction with ACL the past couple of years, which is focused on this idea of learning representations of language, specifically general purpose representations, right? So we want representations of words and phrases and sentences that are capturing something about language that is task independent. So specifically is capturing broadly useful features about language and meaning. So these aren't features of language that allow you to translate well or to parse well or to do sentiment well, but they're something that is intrinsic about the meaning of language that can be applied to very large range of downstream tasks. And kind of importantly, tasks that we don't know exist yet, right? So we're trying to capture something core about what is the meaning of language that allows us to do so many different things with language. And again, the reason I think this is so significant is that this is what used to be two divergent goals between NLP and linguistics have started to merge into very much the same goal. So this is a quote from Richard Montague, who's kind of the father of formal semantics. And he kind of famously started the field of formal semantic study by making this claim that there isn't actually an important difference between human languages like English and Chinese and formal languages like math and logic. And so it actually is possible to understand language using a precise mathematical theory. And we get hung up, I think, sometimes now about what exactly this theory is, but the point is that there's this fundamental belief that you can represent language as math, right? And so it doesn't really matter if it's first-order logic or lambda calculus or some linear algebraic structure, but the point is we're trying to codify language in some way that is algorithmic and reproducible and explainable in terms of math and can be taught to a computer. And that we're trying to do this in a way that is task independent. So it's actually representing something core about the language itself, not in some specific goal-oriented fashion, right? And this process for doing this, for translating language into something mathematical, is very challenging. And as NLP has shifted from saying, I'm going to learn things in an end-to-end fashion or in a task-dependent way, and towards some general purpose representations, we're starting to run into some of these problems that linguists and cognitive scientists have been studying for a while, but we're kind of looking at them in a slightly different way. So I think one that I think is most interesting, or I've been spending a lot of time thinking about, and seems particularly salient right now, is this issue of this trade-off between semantics and pragmatics in language. So I think Sam touched on this actually a bit this morning, but generally when we talk about language or talk about studying language, you begin by acknowledging like there is a world, so there are people and places and things and ideas and all sorts of embodied experiences that people who use language experience. And then language is this very abstract sequence of symbols that we use to refer to the world. And very critically, there is a distinction here, right? There's a line. So we use symbols to represent the world, but these are not one and the same thing. And so we can talk about semantics, which kind of lives up in this space of how do we reason about language and how do we reason symbolically about meaning independent of the world. And then there's pragmatics, which is down here, which is how do we ground the meaning of symbols into the world itself. And most of formal semantic study, and I would argue most of natural language processing, has been primarily concerned with the semantic side of things. So we want to be able to take some text string input that says, I went to the beach over vacation, and decide whether or not one should infer that I laid out in the sun. And we want to do this by just looking at text strings, right? So we very much don't care about the context in which these strings were produced. You don't care who I is. You don't care what the location of the person who's saying this is. You don't care if it was said on a Monday or on a Friday or where they live, whether it was posted on a blog or in a newspaper article, in a face-to-face conversation. All that doesn't matter. You're treating these as symbolic representations, just like text on a page. And this is where this challenge comes in, because as Sam was talking about this morning, and as people are running into more and more as we try to work on these, is it's not clear whether it's possible to reason about these in a purely symbolic way. And so semanticists and linguists and cognitive science have been struggling with this for a while, which is what exactly is a textual inference? What is a semantic inference that we can expect to process by just reading lots of text and reasoning about the way that text relates to each other symbolically? And what is ultimately a pragmatic inference that requires reasoning about the world more generally? So if I'm trying to decide whether I went to the beach over vacation entails I laid out in the sun, can I do this by just processing text, or do I need some model of the world more generally? And if I need the model of the world more generally, how do I represent that, and where does it come in, and how do I encode it, right? So this used to be kind of a curiosity that linguists would debate, and it wasn't that practical for NLP because it didn't really matter when we were working on things in a task-dependent way. You could just learn that maybe there's a relationship between beach and sun that matters in a particular task that you care about. But now we want to build some general representation of the meaning of the word beach. And so we have to decide, or our systems have to decide what belongs within this vector. Like, should it capture that a beach is a location near the water? Should it say that it's a place, or maybe that it's a popular vacation place? Should it capture something like that it's not indoors? Should we start pulling on all of these negative types of meaning representations? Maybe you want it to say something about what a beach contains, so you might want to say it might have palm trees, or maybe you should be more precise, and it should say, what is the probability that something that is referred to as a beach has palm trees in the real world? Maybe you want something that's more language-specific in its representation, which says, I don't care about the probability that a given beach has palm trees, but I care about the probability that when I say the word beach, you assume that it has palm trees, right? So there's a ton of different things you could go on and on and on about what you might pack into a representation for this word. And there's theories and debates and cognitive science evidence to support any number of these different things. So you can talk about dictionary representations. I actually think this is one that there's pretty little support that this is actually what humans have in their head when they think of beach, but it is a possible representation, right? This would fall into more taxonomic representations, and this is actually one that has quite a bit of traction within the NLP community because a lot of our resources have been based on this, and they've proven very useful, right? So you want to record that a beach is a vacation place is a place, and this is kind of hierarchical. You want to encode disjointness, the beach is not indoors. And there has been a lot of work in the past couple years on basically reshaping our vector spaces to capture these types of relations. But it's not given that this is actually what we should be representing. This is an open question, right? Then there's kind of knowledge-based types of inferences. So this is also an area that's been worked on pretty actively in NLP, is building, databases of facts by extracting things from text and modeling the world. And it's a very open question whether a model of the world is a model of language, right? So does the probability that a given beach has palm trees, is that relevant for the meaning of the word beach, or is that a fact about the world? So that's again, an open question. And then actually this is one of my current favorite representations, but again, everything's up for grabs, is the notion of kind of prototypicality in meaning. So it's not so much important that our representations of meaning reflect the world as it is, but more important that we're coordinating with other speakers about what these representations allow the person we're talking to believe, right? So these are what we call prototype types of representations, and it's an alternative theory for what beach should contain. And then finally, you have some, what I also think is a pretty interesting but less well-specified theory, which is something like an encyclopedic representation, which would say that this vector captures some kind of grab bag of facts and information about beaches that are all at your disposal when you're making inferences, but there's no clear delineation between these different types of knowledge that you have, right? And I bring this up not because one of these is right and I think we should be doing it, but because I think that when you start talking about what is the future of NLP and for deep learning in NLP and what are some open problems that we should be looking at, I think one is being really hands-on in these kinds of decisions. So what do we currently represent in our representation of the word beach is a contextual representation. So we know exactly what's in this vector, and it is the probability that beach occurs to the left and the right of every other word in the English vocabulary, right? And this is a representation. It's probably not totally wrong. It's been doing very well for a lot of things. But this isn't like a God-given representation that we have to be using. And I think being clear about what representations we're using, what representations we want to have, helps us better diagnose what weaknesses we might be building into our systems from the beginning, right? Because this acts as raw input into any future downstream NLP tasks. And it's been less important when we can train these vectors in an end-to-end setting. So the particulars of the pre-trained embedding might be helpful, but then you can tune them specifically for summarization and translation and blah, blah, blah. But if we're trying to do this in a task-independent way, suddenly it starts to matter what exactly goes into this vector, right? So I want to pause before I go on to some work we've done specifically about word representations and summarize up to this point what I think is just emphasize that, yes, we should care about linguistics, and this is for a very particular reason, which is not that linguistics has some answers that we should be encoding into our systems, but for the reason that we are at a point now where we're trying to take on a much bigger challenge than we've been taking on in NLP, which is we're trying to represent language, and we should be being very clear and concrete about what theories we're making about our models of language so we can compare strengths and weaknesses of different models at a higher level than just saying, my system does better than your system on this specific data set. Right? Okay, so I want to talk about specifically testing a theory of word representations on some work we did last year. And we were specifically interested in the representation that is the prevailing one in formal semantics and linguistics. So this is called model-theoretic semantics. So like I said, there's not really a consensus, and I think there's a lot of really interesting current work, especially in like cognitive science area, about what is the meaning of the word beach and how is it represented in your head. But there's kind of a false consensus if you ask formal semanticists, and at least 9 out of 10 will say, obviously, I know what the meaning of the word beach is. It's a pointer to things in the world. Specifically, the meaning of the word beach is the set of all the things in the world that are beaches, right? So this is the kind of way that semanticists talk about nouns, is they are sets. So a theory for the representation of beach is that it's a set of things, and specifically, it's a set that gets operated on by other words in the English language. So then you have the meaning of the word Sandy is some function that picks out a subset of the meaning of the set beach, right? So you have beach is a set, sandy beach is a subset of that set, tropical beach is another one, yada, yada. And so this is the kind of go-to model for how formal semanticists like to talk about meaning representations is sets and functions on sets, right? And this has, at various points in time, been brought in more or less to different NLP models. And it's very entrenched within the linguistics literature, but it's again, open whether this is actually the correct model to be using. So one of the reasons that I think semanticists like it so much is that it's very clear in the predictions it makes for how should, what types of inferences are licensed in something like an RTE setting, right? So if I say, well, the set, or beach is a set and sandy beach is a subset of that set, and then I get a sentence like a little boy is doing a handstand on a beach, and I'm trying to decide whether or not I can infer that the little boy is doing a handstand on a sandy beach. Well, there's a very clear answer here, which is there are many beaches that are not sandy beaches. Therefore, this is not a valid inference because there's no reason I should conclude that this beach is a sandy beach, right, without any further context. And again, we're in the semantic reasoning space where there's no additional context. So that's a clear set of predictions and a theory. So what we wanted to look at in a paper from 2016 was whether this theory is a good one that we should be building into our systems, specifically how well does it explain human predictions about these kinds of inferences. So we gathered human inferences for about 5,000 sentence pairs that looked like this. They were identical. They had a single word inserted. So we have something like boy doing a handstand on a beach, doing a handstand on a sandy beach. And we asked humans in the same way that we ask our systems, does the premise entail a hypothesis? And they gave a yes, no answer. Actually a sliding scale type of answer, but essentially a yes or no answer. And for example, in this case, our human annotators unanimously disagreed with the prediction of the model theoretic semantics, right? So all of our subjects agreed that if you say a boy is doing a handstand on the beach, it's valid to assume he's doing a handstand on a sandy beach. And actually, out of the data we tested, very, very often human inferences disagreed with the predictions of the model theoretic semantics. So in the news data set, or we looked at several genres, but in news specifically, we have about 35% of the time that the model theoretic predictions disagreed with humans, and it varied a lot by domain. So in image captions, it was about 15% of the time it disagreed, and in the worst case was in debate forums where it disagreed almost 50% of the time, right? So this was an interesting result. It was interesting for us because of this, again, kind of conventional wisdom that set-theoretic semantics is a good way to model semantics, and a lot of the other phenomena we talk about in linguistics, everything from quantification and negation and modification and all these different phenomena that we talk about in linguistics are based on this notion of thinking about language as sets, right? So this doesn't in itself say that that's the wrong one, but it gives us good reason to be skeptical about trying to incorporate all of this set theoretic knowledge into our systems under the assumption that's going to make the predictions we want it to make, right? But what's more interesting is trying to dig into not just saying that this model doesn't make the right predictions, but what exactly are the predictions that it's not making correctly, and what are the ones that we want our systems to replicate so we can try to gain insights into what might be a better model to use, right? So like here's some examples of sentences where humans decided that adding the modifier was entailed, and you can see they're all quite intuitive. So if you say something like, I feel there will be a lack of evidence forthcoming, people infer that evidence implies credible evidence. If you say, Evans grasped his hand and shook it warmly, people assume the hand is an outstretched hand. If you say his body was found a week later, people assume it's a dead body. All perfectly reasonable inferences. On the other side, you also have times where people say, no, that modifier is contradictory, right? So if you say Bush travels Monday to Michigan to make remarks on the economy, then they infer it's not the Japanese economy. If you say government is the only thing holding back large corporations, people say you don't mean small government. If you say a child is riding on a man's shoulders, they say it's probably not a homeless man. Again, also all reasonable inferences. And so the question isn't, I would hope that we all agree we want our systems to be able to replicate these types of inferences if they understand language. So the challenge is deciding how are we going to do that? Where is this meaning going to be stored? Is this something that belongs in word representations or not? So do we want the vector for evidence to encode the fact that it's probably credible? I think there might be some kind of non-negativity argument for saying, like, yes, we want vectors to encode some positive aspects about likely assumptions about those things. That might be okay. But what about saying that the vector for economy should encode that it's not Japanese? Like, that seems kind of bad. Or for the vector for body to encode that it's dead. Also probably not great. So we end up with this kind of gradation of inferences that we want our systems to make. Yeah. Because it wasn't, absolutely. And I think all of these, to some extent or another, are in context, right? And this is exactly the issue, is that this inference is being made, and it's hard to pull out exactly what is permitting this inference. Is it, so again, we're trying to think of how are we going to build these representations to be reusable. So do I want this lack of Japanese-ness of the economy to be a property of economy, to be a property of Bush, to be a property of the composition between economy and Bush, to be some further external knowledge base that gets brought in at runtime, right? Like, so we have to make decisions about that kind of thing. And this is exactly this issue that gets debated when linguists are talking about how do we codify language, is where do we draw this line? What is a property of the word? What is a property of the syntactic role of the word? What is a property of the sentence? What is a property of larger context? And what is really a property of a purely pragmatic property that requires some embodied state, right? And so deciding where to draw this line, again, is starts to feel less like a theoretical problem and more like a practical problem for actually building systems to understand language. But again, so I was getting very excited thinking about these things, and a lot of people who really enjoy thinking about language really like to think about these things. But it's worth taking a step back and again asking, like, should we care about this at all, right? Like, this seems very cool and interesting. You can pull out examples, but there's also this kind of pejorative notion of the armchair linguist, right? Who's like sitting there and like stroking his beard and like, where is the semantics-pragmatics divide? And it's not clear whether this is something that is important or is purely theoretical and philosophical, or is this something that is actually important for building NLP systems? Yeah.
Again, I'm sorry, like it seems that it's weird to put a 1D, like, oh, there's a divide somewhere, right? Like, this isn't a 1D, it's not a 1D issue where there's a line somewhere and, you know.
I completely agree with you.
Framing of, oh, where do we draw the line?
I completely agree with you that there's not a clear line, right? Everyone.
It's not in a 1D thing.
I was restricted by the limitations of presentation to not have some n-dimensional represent, but I agree. Given infinite, I would have represented something more beautiful here, right? Okay. So the issue is this something we really need to care about? Do we have to make clear decisions about this? Maybe systems can learn it automatically, right? Like, given the right enough training data and the right objective function, maybe they'll just figure out in what n-dimensional space this decision belongs, right? And we don't have to decide. So we tried testing that specifically in the context of this RTE task. So recall that here we have systems that take as input a pair of sentences, and they output true if the premise entails the hypothesis, false otherwise. We frame it as a binary classification. Some people do a three-way classification. Here we do binary. And so this is a task that's been studied, and there is data for this where you have pairs of sentences. And we're specifically going to define a simplified task, which is kind of a subtask of this general task. And it's exactly the same, pair of sentences, true or false output. But we're imposing this restriction that the only difference between sentence 1 and sentence 2 is this one additional modifier that's being inserted, right? And we want to see whether systems that are trying to learn how to do or RTE generally can, in the process, kind of figure out this modifier noun composition piece for free. So we collected human labels for a little over 5,000 pairs that differ by this single modifier. We use about 5,000 for training, and then we have a little under 400 that we're using for testing, and these have been vetted because there's definitely some lack of consensus on some pairs, so these are all ones with high agreement. And then in addition, we have 500,000 sentences from the SNLI data set that Sam described earlier. So these are in the same spirit as our data, as in they're a pair of sentences, and you want a true or false output, but they're different in that they might differ by any number of words, not just the single word that we're adding in. So here's some results. This was, our data set's pretty skewed, so if you always say false, if you always say non-entailment, you get 85% accuracy. And a very, very achievable accuracy is 92%, which is what you get if you just recognize what modifier is being inserted and memorize the most likely class for that modifier. So if you say every time credible gets inserted, more likely than not, it's an entailment. Every time Japanese gets inserted, more likely than not, it's a contradiction or a non-entailment. That's not, we would like systems to do something more than that, but if you at least do that, you get 92% accuracy. So we tried several things, bag of words model, kind of summed over vectors model, RNN, LSTM, and nothing gets notably better than what we get when we just always say false. What's most significant is that even when we do this transfer learning setup, right, when we pre-train on 500,000 sentences and then fine-tune on our 5,000 sentences, we still don't get anything that's really noticeably better than this most frequent class baseline. And this is worth pointing out that this isn't really a data issue. So in a similar setup for transfer learning on the SICK data set, which is another entailment data set that is very similar to the SNLI data set, but similar in size to our data set, so about 5,000 examples. There, when you did this pre-train on the SNLI and then fine-tune on SICK, you got about a 9-point accuracy improvement, and our setup, which was the same, you got a no accuracy improvement. So this doesn't seem to be an issue of not having enough data. It seems to be an issue of the underlying representation that's being learned during the pre-training is not capturing what is needed to do well on this very specific subtask, right? Okay, so I like to end on a negative result, and I'll conclude with just, yes, we should absolutely care about linguistics, and again, not because linguistics has some insight that we should be building into our systems, but because our incentives have now become especially aligned with the interests of linguists. And specifically, we're trying to build these task-independent representations of language. And if we're going to do this well, and if we're going to do it productively and scientifically, we need to start asking and answering questions like, what exactly are the components of meaning that are somehow intrinsic to language? And what are things that necessarily must be determined in context? And what are things that maybe have to be learned in a task-dependent nature? And how do we figure out where the trade-off is and where these different components of meaning belong? And then also, if we're not going to train end-to-end, if we're not going to define our objective as doing well on this specific task, then what is our objective? How do we know when we have the right representation? What tasks should we be viewing as fundamental tasks that we should be training for explicitly and benchmarking on? And which are the ones that we should kind of assume come along for free in the process of doing those things? And this is also an empirical question that I think needs to be actively and concretely hypothesized and tested about. All right, thank you very much.